Welcome back to the deep dive. It is really great to have you sitting down with us again today.
Yeah, thanks for joining us. We've got a really incredible topic today.
We do. We know you're usually tuning in to find that next big perspective shift, right? That little nugget of insight you can take with you into your work or just use to, understand the world a bit better.
Exactly. And today we are heading straight into the microscopic, highly complex, but surprisingly accessible world of custom microprocessors.
It's a space that historically feels, well, it feels locked behind the heavily guarded doors of these massive tech corporations.
Oh, absolutely. The barrier to entry has always been incredibly high, technically, financially, you name it. But the sources we're looking at today show how those doors are currently being thrown wide open.
Before we jump into the deep end, I do need to establish a quick ground rule for this particular deep dive. We are going to be talking a lot about an architecture that is spelled RISC-V, but in the industry, it is strictly pronounced RISC-V.
Right, yes. So every time you hear us reference RSC5 today, just picture that V as a Roman numeral.
It's a small detail, but using the right terminology instantly signals whether you know your way around the current hardware landscape. If you say RISC-V in a meeting, people will politely nod, but they'll know you aren't familiar with the ecosystem.
They definitely will. It's the ultimate shibboleth in processor design right now.
So our mission today is to unpack a brilliant presentation put together by Dr. Chesta Utrafan. He's an associate professor from the VLSI and Embedded System Technology Research Group at Universiti Tun Hussein on Malaysia.
It will just refer to the university as UTHM for short today.
Right. And just to clarify for everyone, VLSI stands for Very Large Scale Integration, which is basically the process of creating an integrated circuit by combining millions, sometimes billions of transistors onto a single chip.
The material he provided gives us this incredibly rare, almost over-the-shoulder look at how to build a custom computer brain from the ground up.
It's fascinating. It takes us from the underlying philosophy through the digital architecture, all the way to testing the physical hardware.
And that's the destination for you today. We are not just going to talk about abstract silicon concepts.
No, we're going to look at the exact blueprints of a custom microprocessor. We're going to understand how it was built to run very specific tasks and reveal the actual numbers on how efficiently it runs in the real world.
Let's start with the foundation, though. What exactly is RISC-V, and why is it causing such a massive shift in how the tech world operates?
At its core, RISC-V is an instruction set architecture, often abbreviated as an ISA.
Right. And for anyone who might be a bit rusty on processor design, you can think of an ISA as the fundamental vocabulary that a computer processor understands.
It's the bridge between the software code a programmer writes and the physical hardware that executes that code.
Exactly. But the true disruption of RISC-V, the reason it's fundamentally changing the industry, is that it is entirely open source.
Because it's open source, anyone can use it, from a university research team in Malaysia to a massive tech conglomerate. You can use this vocabulary, this foundational architecture, without paying licensing fees.
And the economic implications of that are just staggering. Historically, if a company wanted to build a processor, they had to pay these hefty royalties to the corporations that own the proprietary ISAs.
It was a massive financial hurdle just to get to the starting line.
With RISC-V, those barriers to entry simply vanish. It is encouraging a level of global collaboration and rapid innovation that hardware design really hasn't experienced before.
We aren't just talking about a couple of enthusiasts tinkering in a garage either. The presentation explicitly lists the leading industry giants investing heavily in this ecosystem.
We are talking about Google, NVIDIA, Microsoft, Qualcomm, Huawei, Alibaba Cloud, and C5. They are all actively pulling in this direction.
It isn't just the lack of licensing fees attracting these giants, though, is it?
No, it's the architecture itself.
Okay.
RISC-V is explicitly designed to be clean and highly modular. It allows hardware developers to create custom extensions for their specific needs.
So they aren't forced to adopt a massive, bloated processor that has 1,000 legacy features they will never even use.
Exactly. But that brings up a good question. Doesn't stripping away those features limit what the computer can do?
Right, because we are so used to our devices being universal machines, devices that can run a spreadsheet, play a 3D game, edit video all at once. By stripping features away, aren't they losing the flexibility that makes modern processors so useful?
That is the trade-off, and it is a deliberate one. What you get in return is scalability.
Scalability?
Yes. You can take this exact same foundational architecture and scale it up to those massive, general-purpose computing setups in a server farm. But you can also scale it all the way down to tiny, ultra-low power embedded systems.
So think of a single sensor in a smart factory.
Or a vital monitor in a hospital. Those devices don't need to render 3D graphics. They just need to read a temperature and send a signal.
Which perfectly frames the specific goal of the UTHM research group. Their philosophy, as outlined by Dr. Utrafan, is focused on elegant minimalism.
They wanted to design a microprocessor that executes only certain essential instructions for a specific purpose.
The thesis is simple. Less complex hardware leads to significantly reduced power consumption.
To truly appreciate how they achieved this minimalism, we have to look past the high-level philosophy and examine the vocabulary itself.
Right. Traditional complex chips have massive, sprawling instruction sets. The RISC-V vocabulary is built on a very rigid, highly structured format.
Let's transition into that structure. The UTHM team utilized the RV32I instruction set format.
This is a 32-bit format. So for you listening, imagine a digital sentence that is exactly 32 characters long, where every single character is either a 0 or a 1.
Because it is always exactly 32 bits, the processor doesn't have to waste time or logic gates guessing where one command ends and the next begins. It is highly predictable.
And that predictability is key to keeping the hardware simple. That 32-bit sentence is sliced into very specific functional blocks.
At the end of the instruction, you have what is called the opcode. You could think of the opcode as the verb of the sentence.
It tells the processor the general category of the action taking place, like whether it's going to do some math or if it needs to load data from memory.
And once the processor knows what action to take, it needs to know where to put the result. That is handled by a block called a phenide, which stands for the destination register.
Then you need your inputs to perform the action. Those are designated by RS1 and RS2, which stand for Source Register 1 and Source Register 2.
The real elegance of the RISC-V design, though, comes in how it uses the remaining bits. These are labeled Func3 and Func7.
They act almost like toggle switches, right? Or modifiers to the main opcode.
Exactly. This modular elegance really stood out in the source material. The presentation outlines several specific instruction types to show how this works. Let's look at the R-type instructions first.
The R stands for register, meaning these commands deal entirely with moving data between the processor's internal registers. This is where your standard math and logic happen.
The R-type list includes standard arithmetic like ADD and SUB for addition and subtraction. It also includes bitwise logic operations.
Things like XRR or R and E.
And various shift operations that manipulate the binary data directly. SLL, SRL, SRA.
What makes the 32-bit layout so brilliant is that an ADD instruction and a SUB instruction use the exact same fundamental layout.
They have the same opcode, they pull from the same RS1 and RS2 source locations, and they output to the same internal destination.
The only difference is a single change in the binary code of the Func7 modifier block. It's just a tiny switch flipped to tell the computer to subtract instead of add.
Which means the physical hardware required to process both commands can be heavily shared. It's incredibly efficient.
But a processor obviously needs to do more than internal math.
Right. The architecture also defines U-type instructions, things like LUI and AUIPC. These are used to handle larger numbers, essentially loading data into the upper portions of a register.
Then you have the navigational commands, the J-type instructions like JAL, which is jump and link.
This tells the processor to stop what it's doing, jump to a completely different part of the program, and remember where it came from so it can link back later.
And finally, the B-type instructions, which stand for branch. A command like BEQ or branch if equal compares two values.
If they match, the program takes one path. If they don't, it takes another. This is the bedrock of computer logic and decision-making.
With that vocabulary established, Dr. Utrafan provides a simplified block diagram of how the UTHM RISC-V core is physically laid out to process those commands.
Tracing the path is surprisingly intuitive. It all begins at the input port and the program memory, which is where these 32-bit instructions live.
Those instructions flow directly into the control unit. If you think of the whole chip as a factory, the control unit is the dispatcher.
It reads the opcode and those Func3 and Func7 modifiers, and it uses them to route the data to the correct departments.
The actual heavy lifting is done by the ALU, the arithmetic logic unit. This is the calculator part of the brain.
But the data doesn't just flow freely into the ALU. It is routed through components called multiplexers.
The diagram specifically labels these as A cell and B cell, which stand for A select and B select.
Multiplexers function like digital train switches. The control unit tells the A-select and B-select multiplexers exactly which pieces of data are allowed to enter the ALU at any given microscopic clock cycle.
Once the ALU processes the data, the result flows out to the destination register or to the output port.
It is a beautifully clean loop. Input the command, decode in the control unit, route it through the A-select and B-select switches, calculated in the ALU, and push the output.
But designing a blueprint on a computer screen is only half the battle. How do they actually prove this custom architecture works before spending money to manufacture it?
The first step in validation is the simulation phase. Before you burn a design into physical silicon, you test it in a digital environment.
The UTHM team utilized a tool called the CP-Later simulator to test their machine code against their custom architecture.
The specific test program they wrote to verify compliance with the RISC-V specifications was a simple binary counter.
And looking at the assembly microcode for this counter is a great reminder of how meticulous software engineering has to be at this foundational level. You aren't dragging and dropping app icons, you are manually managing the flow of electricity.
Let's walk through the narrative of this code without getting bogged down in the raw hexadecimal text. The first thing the program has to do is establish a connection to the outside world.
Right. The programmer writes a line of code.ly T00X90 that essentially says, hey, processor, look at this very specific memory address, address 90 in hexadecimal.
They do this because, in their hardware design, address 90 isn't just a storage space. It is physically wired to the UTHM RISC-V output A port.
It's called memory mapped output. If you push a number into that specific slot, it physically sends voltage down a wire. Next, they need a starting point. So they command the processor to load a value of 0 into a working register using LY-T1 0.
Once the 0 is loaded, the next instruction explicitly tells the processor to write that 0 out to the physical address we just set up. That's the SBT10T0 command.
Now here is where we hit a practical problem. A microprocessor operates at millions of cycles per second.
If it just started counting, the numbers would blur past instantly. Human eyes can't process an LED blinking millions of times a second, so they have to introduce a delay.
They use a jump and link command JALRA delay to pause the counting process. It's a bit like dealing with a hyperactive toddler.
You have to explicitly tell the processor to go to this other corner of the room, count to 10,000 silently, and then come back here before you say the next number. Otherwise, the output is just a blur.
Once the delay routine finishes and links back, the main loop executes. The processor takes the current number, routes it into the ALU, adds 1 to it with ADDI T11, takes the new total, and pushes it back out to the physical wire.
Then it hits another jump command JAL X loop that loops the entire process back to the start.
What is profound about this simulation is seeing how these tiny, highly structured 32-bit sentences dictate the physical reality of the chip.
Every time the code loops, the control unit fires, the A-select and B-select multiplexers shift the data, the ALU performs the R-type addition, and the new reality is pushed out to the port.
But a digital simulator is still just software pretending to be hardware. It operates in a perfect environment. The absolute focal point of this entire project is the physical, real-world hardware validation.
The physical world is messy. It introduces electrical resistance, heat, and timing delays that a simulator might miss. To validate their custom RISC-V core, the UTHM team implemented their design onto an FPGA.
Specifically, they used an Altera Cyclone V FPGA mounted on a DE1 SoC development board.
If you aren't familiar with hardware development, an FPGA, which stands for Field Programmable Gate Array, is essentially a blank canvas of silicon.
Unlike a standard processor where the physical wires are permanently etched into the silicon, an FPGA allows you to program its internal logic gates to behave exactly like the custom processor you just designed.
It turns a digital blueprint into a physical circuit. To make the results of their binary counter tangible, the team physically connected the output of their newly minted processor to the 8 LEDs located on the Altera board.
They also wired it to a 7-segment display, which provides a much clearer numerical presentation of the counting process as it increments.
You literally see the lights blinking and the red numbers ticking up, driven entirely by this hyper-minimalist, custom-built brain.
But as satisfying as the visuals are, the real triumph of the UTHM project lies in the data they extracted from this physical test on the Altera Cyclone V FPGA. Let's dig into the resource utilization.
The presentation notes that their custom design utilized only 24% of the available logic resources on the FPGA.
That number requires a bit of context. The presentation emphasizes a crucial detail. That 24% utilization is mainly driven by the memory required to store the program itself.
If the total footprint is 24%, and the vast majority of that is just the storage space for the instructions, what does that tell us about the actual processing hardware?
It reveals that the data path, the control unit, the A-select and B-select multiplexers, the ALU uses an almost negligible fraction of the FPGA's physical logic resources. The processing core itself is incredibly lightweight.
And that lightweight footprint leads directly to the most impressive metric in the entire presentation: power consumption.
The hardware validation reported a dynamic power dissipation of just 175 milliwatts while operating at a clock speed of 25 megahertz.
Let's anchor that number so we can really appreciate it. A standard desktop computer processor, the kind running a complex proprietary instruction set, often operates at 65 watts or higher under load. Some high-end chips pull over 100 watts.
This custom UTHM chip is running at 175 milliwatts. That is 0.175 watts.
We are talking about a processor that uses roughly 1/300th of the power of a standard desktop chip. You could run this architecture on a tiny coin cell battery for a remarkably long time.
When you synthesize these metrics, the massive reduction in logic utilization and the incredibly low dynamic power draw of 175 milliwatts at 25 megahertz, it serves as the ultimate validation of Dr. Utterfan's core philosophy.
While relentlessly stripping the processor down to only the essential RISC-V instructions required for the task, the hardware complexity plummets. And as a direct result, the power consumption drops to almost nothing.
It perfectly illustrates the concept of form following function. They didn't try to build a universal machine, they built exactly what the task required and achieved a level of efficiency that a general-purpose processor simply cannot match.
It also proves how accessible this technology has become. You no longer need billions of dollars in research and development or massive licensing budgets to design and validate custom silicon.
It brings our whole journey today full circle. We started by unpacking the disruptive, open-source nature of the RISC-V architecture.
We saw how its modular 32-bit vocabulary allowed the UTHM researchers to build a highly specific, ultra-low-power custom chip from scratch.
We followed the logic of the assembly code and watched it transition from a perfect digital simulator into physical reality on an Altera Cyclone V FPGA, specifically the DE1 SoC board, proving its worth with that incredibly tiny power draw.
The barrier to entry for custom hardware has effectively been shattered by the open source community.
Which leaves us with a final, lingering thought for you to mull over as you go about your week. If an open-source architecture allows university researchers to build incredibly efficient, customized processors that use only a fraction of a standard chip's logic.
And they can do it without paying a single dime to the traditional gatekeepers.
Exactly. What does the future look like for the closed-door silicon monopolies? What happens in the next 5 to 10 years when every smart device, every agricultural sensor, and every appliance in our homes is running on community-driven, hyper-specialized brains that cost pennies to make?
The hardware revolution is already here, and it is open source.
Thank you so much for joining us on this deep dive. We will catch you on the next one.